Boeing is all about connecting the world and soaring to new heights in every sense of the phrase. Nestled inside this giant is a large team working on using quantum computing for material science and quantum sensing for navigation. Find out just how soon quantum applications will be up in the air in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Chief Scientist for Disruptive Computing and Networks at Boeing, Jay Lowell. Welcome to the show.
Hey, thanks for having me.
Yeah, it's great to finally get you on here. We've known each other a little bit here. We've met at several CQE events and things. And Boeing is quite impressive in the quantum space. For quite a few years now, you've been generating some news. So I wanted to talk about all the exciting things going on at the company. But first of all, just if you want to give our listeners a little background on how you got interested in quantum computing. I know your background is obviously in physics, but how you got here.
Boy, that's a long answer. So let me give you the very short, the short abbreviated version of that. I am trained as a physicist. I actually was in the military. I went to the Air Force Academy and studied to be a physicist in the Air Force. But ended my career at DARPA as a program manager. And while I was at DARPA, I had a number of programs in quantum technology space, including some that were, and worked with some of the original quantum computing and quantum information science research programs that DARPA had. Some of my programs that I ended up funding while there were developing, for instance, quantum sensors for navigation, some methods of doing quantum nonlinear optics that are turning out to be useful in some of these quantum networking protocols and domains. And a program to do quantum simulation that ended up producing a lot of the underlying technologies that are used by neutral atom and ion trap quantum computing. A lot of the control systems and laser control mechanisms, a lot of that technology was developed in that program, which set out the ambitious goal to build a quantum simulator to simulate quantum materials using either atoms or ions held in lattices that you could do kind of an analog control of that system, create a Hamiltonian, make it work like an analog to the quantum material you're trying to model, and search for novel quantum materials. It was a really ambitious program, and really was kind of a nice way to walk out and end my career at DARPA. I then came what I call as my 7 years in the desert, where I kind of walked away from that field. I went and worked in software. I came to work for Boeing. And coming to work for Boeing, I worked in the commercial airplane side of the company more than I, kind of worked in this quantum technology space. Did work on a number of things: battery safety, electromagnetic effects, so how we protect our airplanes against lightning strikes, and actually factory automation technologies for building and assembling our airplanes. But around about the end of 2018, beginning of 2019, my current boss was, and the CEO of the company were looking at ways to basically for the company to place bets on long-term technologies that we wanted to develop. And quantum technologies was one of those that came up. And I was one of the few people in the company who had a background and expertise in not just that technology area, but in actually developing technologies relevant to that area. And so he brought me in as the chief engineer for this organization. And that started essentially what's now a 3.5-year run in building up the capabilities of the company and really starting our journey to developing quantum technologies that we feel will help our company move into the future. So like you said, it's been a long, winding road and a very interesting journey.
And what's really interesting is it sounds like everything you did at DARPA, it's like cut and paste, drop it onto Boeing several years later, and you're doing that same kind of general theme again, where like developing
Similar.
materials, and then of course the quantum sense that we'll get to today. It sounds like you're covering both areas, right?
Similar. There are a lot of similarities, but there are very distinct differences as well. Some of the things that we're doing at Boeing are really capitalizing on capabilities that we have within the company that are unique. Or at least we feel they're unique, and we feel that they give us an opportunity to get ahead of the field and really make a contribution by leveraging that capability. The other thing that's really somewhat unique is that we have a whole host of efforts that I would say are really kind of inward focused. A lot of you've heard me talk about our quantum computing applications team. That team really in the end is focused on how we internally are going to be able to use the quantum computers as they develop, and understanding how to align that to really the mechanics of how our company works, how we engineer our products, how we develop materials and qualify those materials, how we model and simulate our products to understand their performance and really understand how, kind of the design decisions we have to do. Those are the things that we've been addressing in our compute applications team, which is very different than the approach that I took at DARPA, which really is, if it's generally applicable to developing advancing the field, that's something DARPA was willing to invest in. And here we really have focused on activities that are going to either help us develop technologies that we see have a use in our business, or help us make our business more effective, more efficient, and really better. So it's the areas are similar, but why we're in those areas is very different, and it results in very different projects that we're funding and very different activities that we end up doing.
So in the quantum industry, there's usually a lot of like very specialized companies that deal with some aspect of the stack. And then there are customers who need help with a specific problem. And then every once in a while, there are these, like, I guess, leaders in their field that take on quantum, and they end up with a workforce that's rather large and a focus that's rather large. JPMC comes to mind, for example. You can almost say that they have like the biggest quantum company hidden inside of their company. Not really hidden, it's kind of in the open. So how does that look at Boeing? It sounds like you have a pretty decent sized team. So what kind of like categories of like staff do you have dedicated to quantum?
It's hard to say precisely because it changes month to month. We're organized around a portfolio of projects. Mm-hmm. And the complicated reason is because we're organized around a bunch of projects, we actually don't own any of the people. They're not reporting, they don't have a reporting relationship to our organization. We're a project organization. So we essentially define the projects and have the resources to make those projects work and manage those projects. But then we go out and ask for people from our engineering and research organizations who come in and make and do the work for those projects. So it fluctuates because as the needs of the project change, we'll have people who, work for a period of time on a particular piece of a project and then go off and start doing something else. But the general answer is we're kind of steady state funding 30-ish people. Maybe, sometimes a few more, sometimes a few less. Actually 30 that there's more than 30, but 30 is a number I'm comfortable saying. Okay. I have a couple of projects that I'm really not yet able to talk about what we're doing, and I can't really say how big those projects are because I kind of give away, information that we're not yet ready to share. But I have, if I'll give you an example, we had a review of all of my projects for the first time, in-person review last week, and we had about 20 some people come from all over the country and sit down and go through a 2-day project review where we reviewed all of the project's activities over the past year, what their plans are for the next year, and what their technical challenges are, what their milestones are that they're supposed to meet, and then looked for opportunities for collaboration across projects. Where are places that Project A can help Project B? Because, each project kind of lives in its own little world, but we have to take times like that to have everybody kind of take a step, pause, look up, look around, and see what's going on around them. And we found a number of opportunities for projects to help each other go faster by taking a little bit of time to share, hey, we did this and we solved this problem over here, and it seems like it's related to your problem that you're trying to do over here. And maybe we can help each other figure these aspects out, and we're able to do that. And even though I see all these projects, I don't see them at the level of detail all the time that's able to find those opportunities and those little nuggets of collaboration that really takes bringing everybody together and kind of forcing interaction, if you will. It was really it was pleasant to see.
It sounds like a great environment for people who are looking to expand their skills. Like a lot of our listeners want to know how they can get involved in quantum. And so with different guests, I ask them different paths that they see forward for, let's say, becoming a quantum coder or whatever. So it sounds like you have some kind of system in place for pulling people in and then maybe getting them exposure to something that's new to them that way.
Yeah, we have been. We've been doing that systematically again over the last 3 years. When we started out the organization, we had 5 people. We're now at 30, right? So we've figured out a way to grow by finding people with requisite skills within the company, by hiring people in who have skills that we need. I will say that we're probably, in terms of the people who have a real, a straight quantum background, it's not the majority of the people who are doing work. It's more than half of the people have a non-quantum background working on our projects. And
that's great.
And I feel like it's one of the reasons why many of the projects are successful is because we're bringing in, for example, a lot of times you talk to a small company and they'll have physicists doing everything. If we're working on, say, one of the projects I wanted to talk to you about and I want to highlight is our quantum navigation project. Mm-hmm. So we're going to be demonstrating a fully quantum inertial navigation system later this year. The schedule keeps slipping by a week, so I don't want to throw out a specific date, but we're looking at sometime in June right now, early June. And, we're very excited about this project. But most of the people working that are navigation engineers. They're not quantum physicists. We have one person who's got a quantum background and a bunch of navigation engineers. And that has allowed our team to be very successful because we're focused on making sure we understand how to use that technology in the context of the application that we need to use it for. And that means we need domain experts from both sides. We need people who understand the quantum aspects of the system, but we need people who understand how a navigation system is used, assembled, put together, tested, all of those aspects. That's something that a quantum person can learn, but it's better to take people who do this every day and do it much more efficiently. So I can make much faster progress by staffing that team that way than I can by hiring a bunch of physicists and trying to get them to learn everything that they need to make the project successful.
Yeah, that makes sense. And I guess this seems like a good point to start diving into the main areas of use cases that you're working
Yeah.
on there. And we could start for sure with the navigation. To me, it seems like a very practical application of quantum sensing, right?
Well, it is. It is a very practical application, and fundamentally, it is an application that is critical to the business of the Boeing company. We build things that move, right? That is the the mission of our company is to protect and inspire, connect, protect, and inspire the people of the world. And in order to connect the people of the world, you have to move people from place A to place B. And so those platforms that we build that move things around and connect those people need to know where they are. Fundamentally, navigation is a key enabler for those platforms to be effective. And so that technology is important. And as we build those platforms, we need to make them work in a way that's safe and reliable and extremely effective. And so these quantum navigation systems enable our platforms to navigate in times when GPS is not available or when GPS is degraded without loss of capability. And that's something that has tremendous value to our platforms. It adds a lot of value to those platforms. Therefore, it's an area that the company is fully invested in us being good at. And so it makes sense, right? It's a use case that aligns fundamentally with our business and really forces us to focus on what aspect of the technology we need to develop and how we need to develop it to make it useful for our business. This, to me, is the key to having a good quantum group within a large company, is making sure you understand you're not developing technology because the technology is cool. But it is. You're not developing a technology because it's the new thing. You're developing a technology because you understand how your business needs that technology to work and function a specific way to make your business better.
Yeah, that makes sense. And just high level, obviously we probably can't get too into the weeds, maybe even just for intellectual property reasons. But so you said when GPS isn't available. So this is some kind of like really precise time measurement that's happening?
This isn't about measuring time. This is about measuring forces and rotations.
Okay.
So if you go back to your physics, your first year physics or your high school physics class, you learned kinematics, right? How a ball moves when you fire it through the air, and how you can use equations of motion to predict where that ball is going to be if you know what it's been doing up to this point. And really, in the end, that's what a quantum inertial navigation system does. It uses aspects of quantum sensing to measure the motion, in this case, the motion of atoms, very, very precisely. And in measuring the motion of those atoms really precisely, you're able to understand how your box that contains those atoms is moving through space.
So kind of like a quantum gyroscope.
It is a quantum accelerometer and a quantum gyroscope. It's actually many accelerometers and multiple accelerometers and gyroscopes, but that's the key. Now, we have other sensors that we're going to be fielding as well, but we're actually working very hard to put other quantum sensors on there that work differently, that allow us to essentially map, basically identify where we are by localizing our position on a map, looking at essentially a map of fields, for example, in this case, magnetic fields, and being able to understand where we sit in that area of magnetic field. And we're going to be using all of these quantum sensors together to understand how good can we make a fully quantum navigation system, and how and given that, then how do we go turn that demonstration into a product that we integrate onto one of our Boeing platforms.
So do the sensors remain, does everything remain quantum just within inside that little box? And then there's some kind of like ASIC that converts it to purely classical information to come out, like as an output?
Yes. So the quantum, the volume of the system that is quantum is actually relatively small.
Mm-hmm.
And it's really, it's in all the cases of the sensors that we're fielding, they're using a laser to make the measurement of the quantum system. So you're reading the result of that, that laser probing that quantum system, that set of atoms. And from reading that out, you then have a processor which is doing some calculations and then converting that into the actual, the thing that you really want to measure. So in this case, either a magnetic field or an acceleration or a rotation.
Yeah, that makes sense, because it seems very difficult to implement like a quantum network on an airplane to keep all the information in that state.
No, it's not. These sensors are not going to be networked together in that sense. There's obviously a classical communication network, but that is there to essentially take those readouts and essentially report those all back to a central processor, which takes the net sum of all of those measurements and assembles those into a full picture of where that system is in space at all points in time.
So is the hope to get these kinds of sensors to improve other measurements that go on a plane, maybe pressure, altitude, anything like that?
No, the hope is to use these. Well, we have a couple of different ways that we hope to use them.
Mm-hmm.
But the key thing here is every airplane already has an inertial measurement unit on it. So a set of accelerometers and gyros that help determine the airplane's orientation and accelerations. We think that by replacing that with a quantum unit, we could provide advantages to that platform because it's much more accurate. Therefore, the entirety of the navigation system could handle outages by GPS much more elegantly, much more gracefully. We're not advocating building a navigation system that doesn't actually use GPS. It's foolish to think about building a navigation system that doesn't take advantage of all the resources you have available to determine, well, not all, doesn't take advantage of enough resources that you have available and enough measurements you could make to make that right balance between the performance of the system and the cost of implementing that system in terms of the dollar cost, the volume of the system, the size, the weight, the weight and the power is what typically is, laid out. So within the constraints that we have for the size of that system, we want to maximize the performance that we can get out of it by using the best possible sensors we have available.
Yeah, that's really exciting to have something so real world for quantum sensing. Finally, that's terrific.
We've been working on this project now for a couple of years. So it's been a while it's been in the works for a while. We've been kind of going at it quietly until we were confident things are coming together in such a way that we're going to be able to conduct flight tests that that has been our longstanding goal, which is why we just recently announced that we're going to do this. It helps me put that last bit of pressure on the team that they've got to deliver. And yet they still keep pushing back, saying that we're going to have to delay schedule here and there. But, that's the job of the team, right? The job of the team is to tell me when they're going to be ready to do it. My job is to tell them I'd like them to be ready earlier.
Yeah, I'm already cringing at the thought of some reporter writing a story about this and saying that it's going to take you to a different quantum realm or something when you fly the plane.
No, I hope that that's not the case. Well, that's not really the kind of stuff that we're really interested in. Fundamentally, again, this lines up very well with what we're interested in at Boeing.
Mm-hmm.
The other application we talked about, our compute applications team, is another use case where we really are I think of it as a general use case. We're really looking at many different individual use cases for quantum computers.
Mm-hmm.
The other thing, there are two other areas that we've really been looking hard at. One is in the networking space, in the quantum networking space. Again, the easy way to think about why this is an important use case for us comes back to that fundamental statement. As a company, we build things that connect people together. And you can do that two ways, right? These platforms move, they can actually carry people, but we can also connect them together with networks as a means to ensuring that we're bringing people together with information that they need to have. So we have, for instance, satellites that help, build global communications networks or global sensing networks. And so the intriguing question about quantum networks is how they're going to help things that work that way, how they're going to help make those networked systems better, how we're going to be able to put and deploy quantum sensors that are entangled and basically collaborate together to make those platforms much more effective at the job that we're trying to get them to do. And so we view it as a long-term research area, but we've really tried to lay out research projects that help answer what we see as fundamental questions we need to understand to be able to make a more focused set of decisions in the future about how we would go construct, build, what kind of network we would want to go do. We need to ask the questions now and put the research in place now that give us the ability to make that decision, a year or two from now.
Yeah, and with quantum networks always comes the opportunity to connect quantum computers together and sensors to quantum computers and all these other applications that open up.
We're looking at both, but we're really interested in understanding what are the limitations and constraints around building networks. And so we're trying to put our projects in place to address those aspects. We'll come into whether we want to go do sensing or computing networks, I think later, once we understand better the constraints of the networks themselves, will help us make a decision about which kind of networks we want to build.
Okay, that makes sense. And as far as using quantum computing, I know since around 2020 you've been working, I guess, with IBM systems, right? To work on material science. I don't know if you want to talk a little bit about that, like maybe designing materials for planes and those kinds of applications.
We have been looking at material science and actually, I'd say that's, so we've done really kind of three different studies in material science that we've, are in various stages of maturity. We started off looking at what really turns out to be an optimization problem, but it's an optimization problem of how to optimize aspects of a material. So we're looking at the composite layers in our airplane. So the composite materials in our airplane wings have stacks of carbon fiber that are oriented in different ways. And the fact that these are oriented in different ways is to help make sure that the properties of that material, structural properties of that material, are what we want. Well, it turns out you can't just randomly lay them up. They have to actually obey some rules in order to have essentially a guarantee that those materials will have the properties we want. And so we looked at using quantum computer to solve that optimization problem, that constrained optimization problem of how to find an optimal structure that satisfied all of the rules and was able to basically to do that. We turned out to, had to solve a very large graph problem to do this, graph optimization problem. It was, we're very proud of the result that we were able to do. We collaborated with IBM on that project. I think the preprint is still out. It's hung up in final review for publication in the actual journal, but we hope it's coming any day now. I don't remember where it is exactly. We've also looked at quantum chemistry problem of corrosion, another big material science problem that we have, given that we build these platforms that go into inhospitable environments, is the fact that the metals that compose parts of these planes and submarines and satellites, they corrode over time. And so we have to, right now, a lot of that research into corrosion is fundamentally done heuristically by experiments and by building heuristic models that kind of describe the high-level behavior of what this results in. What we really want to be able to do is have an understanding that connects all the way down to the molecular level, or molecular and atomic level, all the way up to those high-level material behaviors. And so we've been trying to understand how to build chemistry models that have those steps and use quantum computers to solve portions of those chemistry models. That's been a very ambitious project. It's a lot. It turns out there are many stages of the calculation that need to be kind of tightly linked together in order to make this work. And so a lot of the work there has been understanding how to lay out the flow of calculations and how they pass information from one to the other to the next, and really making sure we understand how to go do that and how to build a process and how to build some tools to help us understand that process better and really think about how to tweak and optimize that to the extent that we can. And then lastly, which is more recent, is we've been looking at damage to coatings from a ultraviolet and visible light exposure, looking at the underlying molecular mechanisms that we expect cause this damage, and really trying to figure out if there are ways we can use quantum computers to simulate those behaviors, quantum as well as classical methods, and really trying to investigate these damage mechanisms and really understand how we can make those, again, how we can model these things, how we can use those models to learn how to devise and design better molecules to do that job that don't have these side effects.
So it sounds like you're already going to have some advantage from quantum sensing with that box we discussed.
Yes.
But with these three general use cases for quantum computing, what does your gut tell you might be the first that would give you some quantum computing advantage? Like which of these?
Well, we can kind of see the point where the optimization problem starts to be beyond the scale of the HPC resources we have in-house. That doesn't mean that it's going to be in the community sense, it won't yet be at quantum advantage. But at that point, it's a practical advantage for us, because getting that, kind of getting time on a faster supercomputer than what we have access to is in itself a difficulty. And if we have access to a quantum computer, which we do through relationships that we have with various with IBM and now some other companies as well, if that's faster, well, then it's faster. And so, for a practical sense, I really don't care.
That practical advantage, that's what we call customer advantage. Yeah.
It's very much a practical advantage, right? If the point of those calculations, in the end, the point of those calculations is to be able to keep up with other parts of the design process that are going on simultaneously. And those simulations need to be fast enough that they can keep pace with all that work. And right now, they're not able. We're able to do things that are just small, a little bit smaller than what we want in the classical sense. So those calculations take longer than we would like to keep pace. The quantum computing results, we're not able to do a system that's as large as we're able to do classically right now. But we see, based on our understanding of how these things scale, and some investigation of that, we see a point where it crosses and where it gets to the place where it's now keeping up and maybe even outpacing some of the other calculations. And then we have a different challenge, which is now we have to work on and understand how we rejigger that engineering work so that everything is keeping pace together, like by working on the next slowest thing, right? It's a never-ending bed of nails, right? You hammer one down and you look and there's another one. I got to knock that one down, and you kind of have to keep that going to wring all those inefficiencies out of a long, detailed engineering design process for these platforms and these products. These things take years to build and design, and these processes have to work and have to work reliably. So a lot of our focus has been on understanding and guaranteeing the outcome and really understanding when we need to make a decision about changing how we perform that calculation without loss of that guarantee.
Yeah, I mean, anyone who's flown on the 787 Dreamliner knows what it is to watch the wings bend up out in the sky and everything. That's not subtle. That's like
no,
very noticeable.
It's not subtle at all.
Yeah.
And every time I sit on the Dreamliner, I look at those wings and I just, a warm feeling comes over me. But every bit as warm as the fact that I know that inventions that I've worked on are somewhere else on that airplane, helping that airplane fly because of years of effort trying to devise a better way to do something that's better, faster, cheaper, safer, or a combination of all of those things.
Yeah, and it sounds like in the case of this experiment, maybe just the very next iteration of QPU, I don't know, let's say the next IBM chip, if that's the one, that might be the one that crosses that line, right? It could be. It's possible.
It's probably maybe the next year, but we'll see. It's we're very much a do the work and let the work speak for itself kind of group, which is one of the things I like about our group is that we're data oriented, and really trying to understand. We're trying to be systematic and data oriented about this. We have a clear vision, I think, as a team, and a relatively uniform approach to how all of those projects approach doing the work that they're doing, and that's again been really, really satisfying to see the team grow and to go from just starting to understand what to go do, to building a culture that allows them to work in an effective way, to actually starting to come back and report great accomplishments and even more exciting future. It's been really satisfying to see over the past 3 years. And we're, as a company, we're setting ourselves up for more growth in this space. We're still hiring people. We're going to be hiring people over the next couple of years, we expect. Not super fast, but we'll be hiring people. And that's great to see. It's because we have an understanding of how this is going to be useful. We see what we're going to have to go do to make that work. And that work requires us to be more aggressive and more accomplished over time.
Yeah, and I saw that you donated Boeing donated $5 million to UCLA for quantum science and technology. So it's exciting to see that not only you're a success story basically in making quantum reality in Boeing, but also in furthering that path of development for people coming up the ranks.
As I said, it's really satisfying in that the leadership of the company is committed to the technology. They understand it's one of those things that we need to have out in the future. And they understand that it's a long-term play, right? We're not going to see return this year. We're not going to see return next year. We're going to see things that, help us and demonstrate and give us confidence that we're on the right path. And we may, we've gotten some contract research out of the investments that we've made internally. And that's really good to see. We might be able to get that, but we're in this for the long game. We understand Boeing's a company that thinks in 30-year product life cycles. So we're not scared by some investment or some decision having a lifetime that's more than just around the corner or the next quarterly report. We really think in those kind of long-term, those long time frames, and in so doing, that helps us kind of, again, see that strategy, see what we need to do to make sure that strategy emerges in a way that helps us, and understand how to make decisions along the way that help reinforce that behavior and help position us to be doing what we want to do and make the company a better company and make the world a better place.
Yeah. So with that, I'll thank you so much for sharing these insights into what you're doing there. I was really looking forward to having you come on, so I appreciate it. And good luck with all these projects going forward. Yeah.
Thank you. I really appreciate the opportunity to speak with you today. It's always a pleasure to see you. And sorry we couldn't do this in person. That might have been even more fun. But
yeah, I'm sure I'll see you in person. Yeah.
Have enough sound.
Thank you.
All right. Thanks.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. With about 30 dedicated quantum staff and the ability to rotate additional experts on a per-project basis, Boeing contains one of the larger QIS teams in the industry. Combined with their dedication to education, Boeing sounds like a fertile breeding ground for quantum innovation, and they're even hiring. What is this team bringing to the skies? For starters, they've developed a practical use for quantum sensing. When GPS is unavailable or degraded, another device based on inertial navigation helps pilots know their plane's location in real time. Quantum sensing will enable a more accurate version of this device with accelerometers and gyroscopes that measure the motion of atoms. Quantum networking will also connect the world, and Boeing's exploring how to network and deploy quantum sensors and quantum computers. They're trying to understand the constraints in these early days before they roll out actual quantum networks. On the quantum computing side, Boeing has been working on materials science for about 3 years. It's a different kind of optimization problem that looks to optimize how composite materials are laid out to create structures that satisfy needs such as flexibility or strength. Corrosion is also a significant concern for planes expected to fly for many years or decades. And quantum computers may help solve some parts of chemistry problems and calculations involved in preventing corrosion. There may also be ways to simulate potential future damage to coatings of materials using quantum computers. Boeing has a terrific view of quantum advantage, considering practical advantage rather than benchmarked advantage. If a step in a process becomes fast enough on quantum to show an edge overall, it's a win. They know it's a long game and are no strangers to products with multi-decade timeframes and life cycles. That does it for this episode. Thanks to Jay Lowell for discussing the exciting projects underway at Boeing. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World, and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.